8.1 on page 365 in the book. Okay, and you may want to pause now. You may want to read the problem before you begin to hear the lecture. Okay. Now, in this problem, Kristen Phillips, she is in charge of planning and coordinating next spring's sales management program for her company. So she has to do a few activities in order to put it through. Several activities that she has to done is to select a location, that is activity A, and then to obtain speakers, make speaker travel plans, prepare and mail brochure, and take reservations. Of course, selecting a location and obtaining speakers do not have any predecessors, so those are these two activities, selecting a location and of course a speaker. So these can proceed independently. These activities have to start for the project to start. So this basically signals the start of the project. So let's say that is the starting point. So once you do that, the next activity is to make speaker travel plans. So for that is activity C, is to make this travel plan. So you should have selected the location and the speakers, then only you can plan. So that's why you have these arrows basically leading into that activity C, which is to make the travel plans. And also activity D is to prepare and mail brochure. Again, for that you have to select a location. Of course, you have to also choose the speakers, without which you cannot prepare the brochures and mail them out. So that's why you have the arrows going from there and from activity B into that. Okay. Then to take reservations, for you to take reservations, you should have mailed the brochure out, so that's what leads to that. Okay, now when you do all those things, so this project has come to an end. So here are activity C and D that do not have any arcs leading out from them. So now basically they are the last activities of the project. Let's take an arc from them and put it into this. That signals the end of the project. Okay. Now, this is a notation that we will follow. Activities, we will use a circle to represent the activities. Within the circle, we will name what activity it is and also how long it's going to take. In case of the CPM, it's a deterministic time is what we use. In case of a PERT problem, we will use the average time here. Okay. Then for each activity, we want to compute the early start time. What is the earliest start time for each activity, and also the early finish time for each activity. The relation between the early finish and early start is early finish equals early start plus the activity duration itself. Then also for each activity, when we work backwards, so here we work forwards in order to get this. To get latest finish and latest start times, we have to analyze the project backwards. Okay, now for this, there is how late can an activity finish and yet do not tardy the project, or how late can the activity start and yet do not tardy the project. Okay, so that relationship between the late start and late finish is late start equals late finish minus the activity's duration time. Okay, so these are the relationships that we'll use in building that. Okay, so let's go to this problem here. Activity A would take 2 days, B would take 3 days. No, these are the weeks, I'm sorry. And activity C would take 2 weeks, D would take 2 weeks, and E would take 3 weeks. Okay. Early start. Let's first compute the early start and early finish times. How soon? Okay, I mean, like next to each node, we will have two sets of numbers. Always the top set of number is the early start, early finish. The bottom set of numbers would represent the latest start and latest finish times. Okay. How soon can activity A start? Right now, which is 0. Then how early can it finish? 0 plus its duration 2, which is 2. Okay. Then activity B, how soon can it start? Right now. How early would it finish? So 0 plus 3, that is 3. Now we have the early start, early finish times for both activity A and B. Let's look at C. How early can activity C start? Activity C can start as soon as activity A and B finish. But activity A finishes after 2 weeks, but B would finish after 3 weeks. So you have to wait for B to finish. So the earliest start for activity C then is 3 weeks. If it is 2, then you are done with 2, but B still is in progress. So you got to wait for B. So that's why it is 3 here. Then 3 plus 2, which is 5. So after 5 weeks, you are done with activity 5 and activity C. Activity D, again you have to wait for both A and B to finish. Since B is going to finish later, so the early start for D is 3, early finish is 3 plus 2, 5. Okay, like activity E, the early start is 5 and finish is 5 plus 3, which is 8. So after 8 weeks, activity E would have finished. So the project, every activity has to finish, and activity E is the last one to finish, so it's going to take 8 weeks. So the project finish time is 8 weeks. Now, if you want this project to finish in 8 weeks, and you don't want the project to get delayed or tardiness to happen, then the latest finish time for the project also is 8 weeks. Is also 8 weeks. Okay. So then only the project is going to finish on time, otherwise it will be tardy. We don't want any tardiness. So if latest finish is 8, how late can it start? 8 minus 3, which is 5. So this is the latest start time for activity E is 5. Okay. Then go back to activity D. Now in analyzing or getting the latest start and latest finish time, we process backwards. For early start, early finish, we process forwards. Okay. So now how late can activity D finish and late do not make the project tardy? That is as late as how late the activity E can start, which is 5. So the latest finish for D is 5. 5 minus 2 is 3, that is the latest start. Okay. Now let us get it for C. Okay. For C, the latest finish is 8. Although early finish is 5, it can finish as late as 8, yet the project would not be delayed. So that's why it is 8 here. So latest start would be 8 minus 2, which is 6. Okay, which is 6. Now let's go to activity B. What is the latest start for activity B? Okay, so the latest start for activity C is 6 weeks, but the latest start for activity D is 3 weeks. If the B is not done in 3 weeks, then the project would be delayed. So for 6, 6 is not possible, because definitely D would be delayed and project would be delayed. We don't want that. So that's why between 6 and 3 you choose 3. So latest finish for B is 3 minus 3, which is latest start is 0. Whereas for activity A, the latest start for D is 3, so latest finish for A is 3. Okay, it can be 6 for the same reasons that I just said, and latest start is 3 minus 2, which is 1. Okay. Now, as you see over here, for activities B, D, and E, early start, early finish, late start, late finish times are exactly identical sets. So there is no leeway, there is no freedom, there is no flexibility to kind of do them a little bit later or earlier. But whereas for activity C and A, we have for C almost 3 weeks of leeway here. For A, we have almost 1 week of leeway over here. So these two are not critical in terms of the project finishing in 8 weeks. But whereas activity B, D, and E, it's imperative, it's very critical that they start and finish by that time period. So these are critical activities, and the path that connects these 3 activities is called the critical path. The project finish time is 8 weeks. Now on this side of the project, what I have done here is I have taken the information that we have from here. Like for activity A, B, C, D, and E, what is the early start, early finish, late start, late finish. Then the slack is defined as the difference between latest start and early start, or latest finish or early finish, any set of these numbers that you can take into. So for slack for A is 1, we don't have any slack in B, neither in D, neither in E, but we have a 3-week slack in C. So these two are not critical activities, the other 3 are critical activities. So now this way we know that these are the activities that need very close monitoring and supervision. These two are the activities that can be scheduled a little later, and hence not make the place congested and make supervision hard. So it can simplify the process, and of course, since we can start this project a little later, we can pay on this little later, and hence the money can earn interest while we can make use of that. So that's why it is important to identify critical and non-critical activities. Okay, folks, let me take another problem. Now this time it is 813, which is a PERT problem. So pause the program right here and read through the problem. Okay. Now in this problem there are about 6 activities, activity A through E to be finished. Okay, not 6, I'm sorry, 5 activities that need to be finished, but for each activity we are given the optimistic time, most likely, and pessimistic time. Use the formula and first compute the average processing time, which is nothing but the optimistic time plus 4 times most likely plus pessimistic, divide that by 6, and that's the result. And you can see the formula right there. Okay, and then copy the formula down to get the average time for each one of those activities, and of course at the same time compute the variance, which is the difference between pessimistic and optimistic. Divide that by 6 and square the result, so that's the variance right there. Okay, and so compute the variance for each one of those activities and represent the network. Look into the problem and then develop this project network and label each one of these activities, and the arrows leading from one to the other captures the precedence requirements that are given in the problem, and the activity times that you see over here in these nodes are the average times from here. So just like before, go ahead with getting the early start, early finish, late start, late finish times for this, very similar to the earlier one. So for early start, early finish, you go forward. To get late start and late finish, you go backwards to get that. Then look at those activities that have the same early start or late start as well as early finish, late finish. So these are the critical activities. And in this case, A, B, and C are critical activities. So those activities, the path that connects them is the critical path. And non-critical activities are D and E, and you have some amount of flexibility leeway over there to schedule these activities little later. So the mean project time that we get over here is 10.83 weeks, and what it means is it could take you less than 10.83 or it can take you more than 10.83, and as an average it will take you 10.83. Okay, now the problem also asks us what is the probability of finishing this project in 11 weeks. Okay, because it can take us longer than 10.83 and even longer than 11 weeks. Now to analyze the situation, so we had to look into what happens. Okay, let's say that you go through this project several times, and each time that you go through, note down how long it would take you to finish the project. Then if you plot that result, it looks like a normal distribution with a mean of 10.83. With a mean of 10.83. So in other words, since it's a normal distribution, about half of the times you are able to do it in 10.83 weeks or less. About half of the time it's going to take you longer. So probability of finishing in 10.83 weeks or less is only half, which is 0.5. Okay, now in this case we want to find out what is the probability of finishing the project in 11 weeks. So okay, so that's over here. Now in order to compute that, we have to get the standard deviation of the critical or the project time itself. Okay, now the variance in the project completion is the sum of the variances of the critical activities. Now in this case, critical activities are A, B, and C. You go to the table that you computed before and get the variances for A, then B and C, only those 3 activities, then add them up. This is the variance. D and E variances you should not add, because this is the critical path that controls the length of the project. Okay, length of the project. That's why we take only those variances into consideration. Okay, so that is 0.36. Standard deviation is going to be the square root of that. So let me put the square root over here. So that's the square root sign, square root of 0.36. Now, here you have to compute the standard normal, which is Z, that is defined as the target minus the mean divided by the standard deviation. In this case, the target is 11 minus mean, which is 10.83, and the standard deviation is the square root of the variance, that is 0.36. So Z is computed as 0.28. Okay, so the probability of finishing in less than 11 weeks is nothing but you have to look into the tables to get the value for what is the area under the curve for a z of 0.28, but fortunately the Excel has a formula built into the Excel which is the norm, okay, which is the norm stands for normal, S stands for standard, distribution DIST of G36. So when you invoke this formula, it's going to give you the area under the curve, which in this case is 0.61. So there is a 61% probability that the project would be done in 11 weeks. There is about a 39% probability that the project would take about more than 11 weeks. So, but there is a penalty of $500,000 if the project is done in not 11 weeks. So the probability that the Bill Fredlund has to pay this penalty is almost 40%. Almost 40%. In other words, if this person goes through building 100 projects like this, about 61 projects he would finish in 11 weeks. There are about 39 projects, he would have gone over 11 weeks, would have paid $500,000. So the long run average expected, so the expected penalty then is 0.39 times 500,000, which equals 0.39 times I made a mistake over here. That was 0. Which is about $195,000. $195,000. Okay. Now clearly, if John basically if Bill wants to kind of win this contract, this is a pretty poor performance in that case. So he has to improve the probability of finishing the project in 11 weeks. One thing is to go and then see in these activities A, B, and C, which one of them has or you can work on them. Okay, C has 0.25 variance, A has 0.11. If you can reduce the variance in these projects, then it can take little less time to finish the project, and you can improve the probability. Let's say that if you can change this to 4, for example, not 4, let's say 5.5, and if you can change the most likely by educating the people or maybe getting some extra help to 4.5, now the mean completion time is 4.42, the variance is 0.17. Okay, and now the project time would be 4.42 is what you would use in place of 4.83. So the project would be done in 10.42 weeks. This is still 10.17, not a binding. 10.42 is what we'll get here. 10.42, and the variance now is 11 plus 17, which is 0.28. Okay, so now the probability can be improved by this much. So what did we say here? We said 10.43, and this is 28 over here. So that is 1.08. Now the probability jumps to 0.86. So from 61%, by doing a little bit of that, now he has improved the probability of finishing the project to 0.86. And likewise, of course, this number would be different. Now it is 0.14 times 500,000. So his expected penalty would also go down to $70,000, from $195,000 to $70,000. So once you have a basic model as a spreadsheet, now you see the power of spreadsheet modeling. You can do this what if activities and see what set of actions would lead you to a better solution. Okay, so this concludes our discussion with respect to this chapter 8. Of course, there is more to talk about in this chapter. Like project crashing, and for that we have to develop a linear programming problem that would help us identify which activities should be selected to cut down their activity time, and of course, how much that would cost, whether we can keep on reducing the project time or not, whether it's feasible and not. Those questions we had to address, and the cost management and all. So as I said before, this is a fairly detailed topic, lengthy topic, and can be easily consume a whole semester if you want to go in details. So the homework that I have assigned to you, go through that and see how well you do on that homework, and I will post the homework solution after I grade and return it back to you.